5.2 Sigma Notation and Limits of Finite Sums. The outline of this video is as follows. We will begin by introducing a compact and powerful tool called Sigma Notation, which allows us to write long sums in a very efficient way. This will be essential for managing the calculations involved in area approximations. Next, we will establish several key algebra rules for working with these finite sums. These rules will give us the ability to manipulate and simplify complex summation expressions, which is a crucial step before we can analyze them further. After that, we will explore the concept of limits of finite sums. This is where we bridge the gap from approximation to precision, by investigating what happens as the number of terms in our sum approaches infinity. Finally, we will formalize this entire process by defining Riemann sums. This involves understanding partitions of an interval and the norm of a partition, which gives us a rigorous framework for calculating the exact area under a curve. Our main goal is to move from inexact rectangular approximations to a precise, single value. When we approximate quantities using finite sums, we often deal with sums containing many terms. Sigma notation provides a compact and powerful way to write these long additions. The expression shown here represents the sum a sub 1 plus a sub 2 plus a sub 3 all the way up to a sub n. Let us break down the notation. The large Greek letter is a capital sigma, which stands for sum. The letter k is called the index of summation. The number below the sigma, k equals 1, is the lower limit, which tells us where the index starts. The number above it, n, is the upper limit, telling us where the index ends. The expression to the right, a sub k, is the formula for the k-th term. We generate each term by substituting the integer values of k from 1 to n into this formula, and then we add all the resulting terms together. A key point is that the lower limit does not have to be 1, it can be any integer. This notation gives us a clear way to define any finite sum by simply specifying its starting point, ending point, and the rule for generating each term. This slide illustrates a key feature of sigma notation, its flexibility. The same finite sum can often be expressed in multiple equivalent ways. Let us focus on example 2. Which considers the sum of the first 5 odd integers, 1 plus 3 plus 5 plus 7 plus 9. One way to write this is to start our summation index, k, at 0. In this case, the formula for the terms is 2k plus 1, which is 0, the term is 1, and when k is 1, the term is 3. To get all 5 terms, the index must run from 0 to 4. Alternatively, we could start the summation at k equals 1. If we do this, the formula for the term must change to 2k minus 1. Now when k is 1, the term is 1, and when k is 2, the term is 3. To get the same 5 terms, our index must now run from 1 to 5. This shows that the starting index, the ending index, and the formula for the terms are all linked together to produce the same final sum. Just as we have rules for algebra, we also have rules for manipulating finite sums, which are essential for simplifying complex expressions. This slide presents 4 fundamental properties that allow us to break sums apart or pull out constants. First, the sum and difference rules state that the sum of terms that are themselves added or subtracted can be split into 2 separate sums. For example, the sum of the quantity a sub k plus b sub k is equal to the sum of a sub k plus the sum of b sub k. Next, the constant multiple rule allows us to factor a constant out of a summation. If every term in a sum is multiplied by the same constant c, we can pull k outside and multiply it by the result of the sum. Finally, the constant value rule handles the simple case of summing a constant value k over and over. If we add the number c to itself n times, The result is simply n times c. These four rules are the basic tools we use to rearrange and evaluate summations. Let us make these algebra rules more concrete with a few examples. In the first example, the sum of the quantity 3k minus k squared is split into two sums by the difference rule. Then, the constant multiple rule allows us to pull the factor of 3 out in front of its summations. In the third example, the sum of k plus 4 is separated into the sum of k and the sum of 4. The sum of k from 1 to 3 is 1 plus 2 plus 3. The sum of the constant 4 over 3 terms is simply 3 times 4. Adding these results gives 6 plus 12, which equals 18. The last example is very important. We are summing the term 1 over n. Because the summation index is k, any other variable, like n, is treated as a constant. So we are adding the constant value 1 over n to itself n times. The result is n times the quantity 1 over n, which simplifies to 1. The key takeaway is that these rules let us algebraically rearrange and simplify complex sums. This slide presents 3 essential formulas for evaluating common finite sums, which are the key to calculating the exact area under curves. The first formula, famously discovered by Gauss, is for the sum of the first integers. The sum from k equals 1 to n of k is equal to n times the quantity n plus 1, all divided by 2. The second formula is for the sum of the first n squares. The sum from k equals 1 to n of k squared is given by a fraction. The numerator is n times n plus 1 times 2n plus 1, and the denominator is 6. Finally, the third formula is for the sum of the first n cubes. This sum from k equals 1 to n of k cubed has a nice connection to the first formula. It is simply the square of the sum of the first n integers. These formulas are powerful tools. They allow us to take a lengthy summation and replace it with a compact algebraic expression that only depends on n, the number of terms. So far, we have used finite sums to approximate area. Now, we will see how to find the exact area by taking the limit as the number of rectangles goes to infinity. Let us work through a concrete example. We want to find the area under the curve y equals 1 minus x squared, specifically on the closed interval from 0 to 1. Our strategy is to slice this area into a large number, n, of thin vertical rectangles, all with the same width. Since the total interval has a length of 1, the width of each rectangle, which we call delta x, is simply 1 over n. This division creates n subintervals. The first one goes from 0 to 1 over n. The second goes from 1 over n to 2 over n, and so on, until the very last rectangle covers the subinterval from n minus 1 over n to 1. With this setup, we have a general framework for our rectangles, no matter how large n gets. To find a lower bound for the area under the curve, we will set up what is called a lower sum. This means we construct a series of rectangles that all fit entirely underneath the function's graph. The key observation is that our function, f of x equals 1 minus x squared, is a decreasing function on the interval from 0 to 1. Because the function's value is always going down as x increases, the lowest point in any given subinterval will always occur at its right endpoint. For the k-th subinterval, this right endpoint is located at x equals k over n. Therefore, we use the function's value at this point as the height for our k-th rectangle. This height is f of k over n, which equals 1 minus the quantity k over n squared. The width of each rectangle is 1 over n. The total area, which we call the lower sum S sub n, is found by summing the areas of all n rectangles. The expression shown here is the complete formula for this lower sum, which simplifies to the sum from k equals 1 to n of the quantity 1 over n minus k squared over n cubed. Now we will simplify our expression for the lower sum, s sub n, by applying the algebra rules for summations. Let us look at the first term. We are summing the quantity 1 over n times. Since 1 over n is a constant with respect to the summation index at k, the constant value rule tells us this sum is simply n times 1 over n, which equals 1. For the second term, the fraction 1 over n cubed is also a constant factor. Using the constant multiple rule, we can pull it outside the summation. This leaves us with 1 over n cubed multiplied by the sum of k squared from k equals 1 to n. This sum of squares is a standard result, so we can substitute its known formula, which is the fraction n times the quantity n plus 1 times the quantity 2n plus 1, all divided by 6. After expanding the terms in the numerator, our sigma notation has been converted into a single rational expression that depends only on n. We now have a closed-form expression for the total area of the n rectangles, which is the crucial step before taking the limit. Now that we have a general formula for the lower sum, we can find the exact area under the curve by taking the limit as the number of rectangles, nn, approaches infinity. This is equivalent to letting the width of each rectangle approach 0. We start with our expression for the lower sum, s sub n. The limit is 1 minus the limit of the fraction 2n cubed plus 3n squared plus n, all divided by 6n cubed. To evaluate this, we can split the fraction into 3 separate terms. This gives us the limit of the quantity 2 over 6 plus 3 over 6n plus 1 over 6n squared. As n becomes very large, the terms with n in the denominator approach 0. So, the second and third terms vanish in the limits. This leaves us with 1 minus 2/6, which simplifies to 1 minus 1/3, or 2/3. This result is the exact area. It is also important to note that if we were to repeat this entire process using the upper sums, we would find that they also converge to the very same value of 2/3. To handle more complex functions, we now generalize our approach for approximating area using a method called the Riemann sum. This powerful framework, formalized by Bernhard Riemann, begins with any bounded function defined over a closed interval from a to b. An important point is that the function f can have both positive and negative values, which will affect how we interpret the final result. The most significant change from our previous method is how we divide the interval. We partition the interval from a to b into smaller subintervals, but critically, these subintervals do not need to have the same width. For example, we could use many narrow subintervals in a region where the function changes quickly, and fewer, wider subintervals where the function is relatively flat. The main takeaway is that this flexibility to use non-uniform widths is the essential new idea that makes Riemann sums so powerful. To make our area approximation method precise, we first need a formal way to divide the interval from a to b into smaller pieces. This is accomplished using what we call a partition. A partition, which we label with a capital P, is simply a set of points along the interval. We begin by relabeling the endpoints. The starting point, a, becomes x0, and the ending point, b, becomes xn. Then, we place n-1 additional points between them, labeled x1, x2, and so on, in strictly increasing order. This collection of points effectively chops the original interval into n smaller, side-by-side subintervals. The kth subinterval is the closed interval from xk-1 to xk. The width of this kth subinterval is denoted by delta xk, and it is calculated as the difference between its endpoints, xk minus 1. A key point is that these widths do not have to be equal. In short, a partition is the formal structure we use to define the bases of the rectangles for our approximation. This slide presents figure 5.8, which shows the general type of function we will be working with to define the definite integral. We have a continuous function, y equals f of x, over a closed interval from a to b. The most important feature to observe here is that the function is not required to be positive everywhere. Notice how the curve dips below the x-axis for part of the interval. In this region, the value of f of x is negative. This is a critical point to keep in mind. As we move forward to approximate the area between the curve and the x-axis using rectangles, this will lead us to the concept of assigned area, where regions below the axis contribute a negative value to the total. Let us now formalize our area approximation by defining a special kind of sum. This sum, called a Riemann sum, is the foundation for the concept of the definite integrals. First, recall that for each subinterval we choose a sample point, which we call c-sub-k. Next, we calculate the product of the function's value at that point, f of c-sub-k, and the width of the subinterval, delta x sub-k. This product gives us the signed area of a single rectangle. The area is positive if the rectangle is above the x-axis and negative if it is below. Finally, we add up these signed areas for all the rectangles from k equals 1 to n. The result, S sub-p equals the sum of f of c-sub-k times delta x sub-k is the Riemann sum for the function f. The value of this sum depends on both the partition P we choose and our selection of the sample points c-sub-k. The Riemann sum gives us a numerical approximation for the net area between the curve and the x-axis. So far, we have mostly considered functions that are above the x-axis. But what happens when the curve dips below it? This is a critical detail for understanding what a Riemann sum truly represents. Remember that each term in the sum is the product of the function's value, f of ck, and the subinterval's width, delta xk. The width, delta xk, is always a positive number, since it is a length. This means the sign of each term in the sum is determined entirely by the sign of f of ck. If the function is negative at our sample point, the corresponding rectangle extends downward, below the x-axis. The product of this negative height and the positive width results in a negative value. This value is the negative of the geometric area of that rectangle. Therefore, any part of the function that lies below the x-axis contributes a negative value to the total Riemann sum. To improve our area approximation, we need to ensure all our rectangular subintervals are thin, even if they have varying widths. We can control this by focusing on the single widest subinterval in our set. This leads to a new concept called the norm of a partition. The norm, written with double vertical bars around the letter P, is defined as the width of the widest subinterval. To find it, you simply look at the widths of all the subintervals in the partition and pick the largest one. For example, if your subinterval widths were 0.2, 0.4, and 0.5, the norm of that partition would be 0.5. The key insight here is that if we force the norm to become very small, it guarantees that every single subinterval in the partition must also be small, since none of them can be wider than the maximum. This gives us a rigorous way to talk about the partition becoming finer. Let us make the concept of a partition's norm concrete with a specific example. The norm is a single number that tells us the width of the widest subinterval in a partition, which is a measure of how fine the partition is. Here we have a partition P of the closed interval from 0 to 2. The points in the partition create 5 subintervals. Our first step is to find the length, or width, of each one. The width of the first subinterval is 0.2. The second is 0.4. The third is also 0.4. The fourth subinterval has a width of 0.5, and the fifth also has a width of 0.5. Now we simply look for the largest value among these 5 widths. The largest value is 0.5. It is important to note that 2 different subintervals can share this maximum width. This is perfectly acceptable. The norm of a partition is determined by the single widest subinterval, so the norm of this partition P is 0.5. This slide presents figure 5.10, which provides a visual intuition for the limiting process that defines the definite integral. On the left, in panel A, we see a collection of relatively wide rectangles, giving a rough approximation of the area under the curve. On the right, in panel B, the partition is much finer, meaning it consists of many more, much thinner rectangles. As you can see, the sum of the areas of these thinner rectangles provides a significantly more accurate approximation of the true area between the curve and the x-axis. Making a partition finer is precisely what happens when we require the norm of the partition to approach 0. As the width of the widest subinterval gets smaller, all subintervals must become narrow. This concept of refining the partition to improve the approximation is the fundamental idea behind the definite integral. The integral will be the exact value that these sums approach as the partitions become infinitely fine. Let us pause to summarize the essential concepts we have just developed, as they are the building blocks for the definite integral. First, we introduced sigma notation as a compact and efficient way to express the long sums that arise when approximating areas. We also noted that, just like with regular algebra, a set of rules exists for manipulating these sums. The central idea is the Riemann sum, which is a sum of the signed areas of rectangles that approximate the region under a curve. Each term in the sum is the product of the function's height, f of c sub k, and the subinterval's width, delta x sub k. To control the accuracy of this approximation, we use the norm of the partition, which is simply the width of the widest subinterval. The key insight is that as this norm approaches 0, our approximation becomes increasingly accurate. This limiting process of the Riemann sum is precisely what we will use to formally define the definite integral. Let us pause here to check our understanding with a few review questions. First, what is the value of the sum from k equals 1 to 10 of the constant 5? Think about the constant value rule for summations. This is simply asking you to add the number 5 to itself 10 times. Second, we have a partition P of the interval from 0 to 10, with points at 0, 2, 5, 8, and 10. What is the norm of this partition? Recall that the norm is the width of the widest subinterval. To find it, you will need to calculate the width of each individual subinterval first, and then identify the largest ones. Finally, consider a function f of x that is always negative over an interval from a to b. Will a Riemann sum for this function be positive or negative? Remember that a Riemann sum is a sum of the products f of c sub k times delta x sub k. The interval widths are always positive, but here, the function values are always negative. Take a moment to work through these before moving on.